All right, we are completing page 18 in your toolkit. First, we're going to look at the different parts of a regular polygon. So here in our diagram, first we will start with W. W we call a central angle. So I'm just going to list that over here. We will solve for that as well. So central angle. Now we find a central angle by taking 360 degrees and dividing it by the number of sides we have. So in this problem here, we have an octagon. So W is going to equal 360 divided by, we have 8. So that angle is going to be 45 degrees for this example problem here. Okay. Now if we look at X, I'm basically taking W, and X would be basically half of that. So we can say that X, we call it a half central angle. In this diagram, X is a half central angle. And again, we take 360 because if you imagine like a full rotation here, full circle, that would be 360 degrees. So this time we are going to take 360, and it's essentially going to be half of whatever our entire central angle is. So it's 360 divided by 2n, twice the number of sides we have, because we can fit 2 of those half central angles on every side. So in this problem here, X is going to equal 360 divided by 2 times 8. So that's going to be divided by 16. Or we could have just said it was half of 45. That works too. So in this diagram, it's going to be 22.5. And that's going to be true for any octagon you work with. The angles are going to be the same no matter what our sides are. Okay. Now the other 2 pieces in the diagram here, we have our Y segment, our Y. We call that an apothem. It's kind of like a fancy name for what I might call the triangle height. So I'll just put that in parentheses. Now, an apothem is the distance from the center of a figure to the middle of one of its sides. So we have essentially in this figure, we'd have 8 of those segments from the middle to the center. This would be another example of an apothem. This would be another example of an apothem. Or this, middle to the center, okay? All right, and then our last segment here, that's Z, we call that a radius of the figure. And a radius is essentially goes from the center of the figure to an angle, a vertex. So we've got, that would be a radius, this length here would be a radius, here would be a radius, here would be a radius, whoops, to the angle would be a radius. Okay, so we can say from center to vertex, or each of the angles. Okay, so we're going to look at a formula that we could potentially use to find the area of a regular polygon. So our formula, the area is going to equal, we're really finding areas of triangles. So we're going to do base of a triangle multiplied with height of a triangle. Now I know a triangle is base times height, all divided by 2. But what I also need to add into that, because we're looking at a regular polygon, is the number of triangles that you have. So number of triangles. So for example, if I'm looking at this diagram here, if I found the area of this entire triangle here, I would say, okay, well, I could fit 8 of those triangles. I could fit 1 of those on each side of that octagon. So I could do the base of this triangle, the height of this triangle, multiply them divided by 2, multiply by 8. Now that becomes a little different if you're finding this little half triangle here. If I was focused on this half triangle, I'd say, okay, well, let me find the base of that, the height, multiply and divide by 2, and then multiply it by 16. I could fit 16 of those triangles into this shape, okay? So just make a note to yourself. You can use half or whole triangles, half or full triangles. So little half triangles I'm more so going to use probably when I have problems that involve trig, having to use sine, cosine, and tangent. So these would be like a little half triangle in the shape. Kind of matches up with the half central angle, okay? Or we can also use the full triangles. And the full triangles would have that full central angle at the middle. So you can like put a W here just as a reminder and an X here. That's how we find each of those angles, okay? And this would be a full triangle. Okay, so let's practice finding the area of some of our figures here. So we have a triangle. Now, technically, we would always want to try doing base times height divided by 2, but for this specific triangle, we do not have the entire height of that triangle. We do know that each side is 31.2. These are all regular 31.2, so all the sides are the same. And what we have is this triangle here. So I'm going to highlight this triangle, and this is what we would call a whole triangle. This angle in the middle, that's a full central angle. Okay, so if I'm looking to find the area of this entire triangle, I have the base of that triangle, I have the height of that triangle, I can do base times height divided by 2, and then I would say, okay, well, I could fit 3 of those triangles into this shape, and this is how. Here's one triangle. If I drew this line in here, here would be a second triangle, and here would be a third triangle, okay? So we've got 3 of those triangles in our shape. So our total area for this shape is the base, 31.2, multiplied with our height, which is 9, divided by 2. Now, if I just did that, that would be the area for this red triangle, but we said we had 3 of them, so I'm going to multiply by 3. So our total area is going to equal 421.2. And since we don't have units here, we'll just put units squared. Okay, and in our next figure, our area. So this time we have a regular heptagon. So all the sides are going to be 7.1, 7.1, 7.1. We don't need to put that on each of the sides. But what I'd like to focus on is, we can do it here, I guess, this triangle right here. Whoops. All right, so I'm going to put the 7.1 here just because I know all of the sides are 7.1s. I'm going to highlight that triangle. I want to find the area of this one triangle here. Well, we know the area would be found doing base times height. I know the base is 7.1. We've got the height as 7.3. I covered that up a little bit. Base times height divided by 2. Now we just need to add in and figure out, well, how many of those triangles will we have? Well, since it's a full triangle, I should be able to fit one of those on each of these sides here. So I should be able to fit 7, the same as the number of sides I have in that figure. So I could do 1, 2, 3, 4, 5, 6, 7. So I'm going to multiply by 7. So that means the area for this entire shape, if we multiply those all together, this will be 181.405 units squared. And when you're putting these into Desmos, let's just do this really quickly. I would make sure when you're setting this up in Desmos, let me move my facial, we can create a fraction here. And so you're going to want to multiply 3 things by each other. You can put them in parentheses and then divide by 2. So I would set that up first and then plug in the 3 numbers that you have there. Okay. And our last problem on this page, we have the area of a regular pentagon with an apothem of 20. And remember, the apothem is like that triangle height. It is the distance from the center of a figure to the opposite side, any of the midpoints essentially. So like this would be an apothem, or this right here, or this right here. There should be 5 of them for this pentagon. Since we didn't write it earlier, you can put from center to the midpoint. That's what the apothem is. It's the triangle height, essentially. So I'm going to put a 20 here on this diagram, and I'm going to create a little half triangle. I'm going to draw this little half triangle in here. Now, anytime you're working with a problem and you're only given one measurement, that tells you are going to need to use some trig to solve for this. So we're going to maybe need to use some sine, cosine, or tangent. So I'm going to write that over here. Remember, sine is opposite and hypotenuse, cosine is adjacent and hypotenuse, and tangent is opposite and adjacent. So we know that this full angle in the middle is 360 degrees. I want to find this angle. It's like a little X angle. That is a half central angle. So X is equal to, it's that half central angle, 360 divided by 2 times 5. There's 5 sides, so twice the number of sides. So I'm really doing 360 divided by 10, which is 36 degrees. Okay, we've got our 36-degree angle. And now what we need is, I want to find the area of this triangle here. So if we want to find the area of this triangle, we also need this side length. The area of this triangle is the base, y, times the height, 20, divided by 2. So in order to do that, we'll set up a trig ratio. I'm just going to draw this triangle off to the side here. Put all my measurements in it. So we've got our 20. Here's our right angle. We figured out that this half central angle was 36 degrees. 36, and this is the side we're solving for. If you want to write this in, you can write half central angle. Okay, so now we've got these two sides here. They are both legs to this triangle. So we're not using sine or cosine. We know that has to be a tangent ratio. We have an opposite leg. That means it's across from 36. We have an adjacent leg. That means it is next to 36 degrees. So opposite and adjacent, that is a tangent ratio. So to solve for y, I could say that the tangent of 36 degrees is equal to opposite over adjacent. Now, if I did a cross product here, y would multiply with essentially 1. 20 would multiply with the tangent of 36. And we will get an approximation for this. So let's put this into our calculator with 20 times tangent 36. And that's going to be 14. I typically will round these to 3 decimal places. This will be 14.531. So now we should have enough information. I put this over here, 14.531. We should have enough information to find the area of this entire triangle, or the entire pentagon rather. So the triangle, that I highlighted blue, the base would be 14.531. The height on that diagram is 20 divided by 2. Now that would be enough just to find that triangle, but then we need to know, okay, well, how many of those triangles fit into this pentagon in total? And there should be 10 of those triangles. And that's because we can fit 2 of them per side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 of them per side. So we can plug this in. Let's practice plugging this into our diagram. So if you wanted to, you could also just take this whole entire number here, copy and paste it, and you can put it here. So we're at 14.531, or you could have copied and pasted that answer. It'll actually be a little more accurate if you do that. Then we're going to multiply by 20, which was the height, and then by 10, because that was the number of triangles that we had. And so our area for that shape is going to be 1,453.1. And that's just going to be in units squared. And that's it.